Okay, good afternoon everybody. Welcome to this very short 30-minute discussion on vibration analysis. Hopefully it gives you a good taster and a visual insight into vibration monitoring. And hopefully at the end we'll just talk about one or two case studies. So we're going to just talk about some theoretical points to start with, very basic hopefully. Talk about the signals we measure, and indeed, as I say, some couple of case studies to talk through. So, our machines talk. They talk to us, but maybe what they don't speak is English or Spanish or German. Obviously, they speak vibration when they are not healthy. You know, it'd be nice if they actually said what was wrong with them, but sadly, that's not the case. But what they do talk is signals. So with vibration monitoring, we can measure the signals, we can measure the height of the signal, and we can measure the distance of the event, how long each event takes to understand which component in the machine is problematic. So we can narrow it down to a specific component within the rotating asset. Here we have a sensor placed on the machine. The forms of vibration that we measure at this particular location could be electrically related. They could be mechanically related to different parts of the machine itself in a mechanical context. We'll talk about those in a moment. And thirdly, there could be a process vibration. So whenever we take a vibration measurement to measure the health and try to track the health of an asset, all of those different considerations could be measured through the signal. And we can separate them out to understand which part of the machine, is it process, is it electrical, or is it mechanical problem we're dealing with. I think a key point to think about with vibration is a couple of things here. Visually is the forces. Think about the forces. The forces here are radially being generated. If I place a sensor radially around this machine, I will measure those forces. Obviously very exaggerated, but if the machine were misaligned like this and it was altered down, that machine is trying to do this in real operation, and that's going to destroy the shaft bearings, the shaft seals, and so forth. So we have to think about the forces. And secondly, think about the motion and indeed the rate of the vibration, the rate at which it moves. We'll look more in a moment about that. Different parts of the machine will vibrate. The heartbeat, the heartbeat of the machine here, if the blades, the way the liquid cuts through the system is disturbed, maybe the pulsation force from the vibration signal we see will produce a different heartbeat to what we saw before. Maybe the volutes in the screw compressor. There will be a certain number of screws here. So we have various screws on each shaft there. The heartbeat of those screws will produce a unique heartbeat. If there's 4 screws, 4 heartbeats per rotation. Obviously much more detailed here maybe, but in simple terms, each gear will have a certain number of teeth. And this defect on one of the teeth, or all of the teeth, or some of the teeth, the heartbeat pattern will be distinctly different, again, to what we saw before, where the machine was misaligned, or secondly, what we saw the volutes or the blades on the pump. So you can see there, obviously, you've got a certain number of teeth on each gear. That will produce a certain number of pulsations. If there's 20 teeth on this gear, for example, 20 pulsations per rotation. So we can trend, we can track that particular heartbeat and measure the health. Maybe with an imbalance, the forces here are more radial again. The force is radial, but it's more of a motional force. Maybe in this context, the heartbeat would produce another distinct pattern. The shaft's bent produces a particular force. Maybe in this situation, we've got more of a shock event or an impact event. So it's going to disturb the signal in a slightly different way to what we've seen before. Maybe with a bearing. If there's a damaged spot on the bearing, it's going to produce a certain number of pulses, impacts per rotation. Maybe the next slide, we can count them. The defect here is where that red dot is at 12 o'clock. 1 shock, 2, 3, 4, 5, 6, 7, 8 and a bit. 8 and a bit shocks per rotation. Not 7, not 8, but 8 point something. That's uniquely different to what we discussed before. Maybe we have a defect here on the outer race, we're not going to count them, but again it's going to produce a unique heartbeat that's different. I guess bringing it into a more complex machine, like a wind turbine, we've got a complex array of rotating components within this system, the hub bearing, the gears, the drive shafts for the generator itself, an epicyclic gearbox with gears that are travelling around. But each part of that machine, each component produces distinct unique heartbeats, and we can trend and we can track those heartbeats and assess the health of each part of that machine. So how does it kind of work? Well, vibration is kind of a strange thing. People think vibration, everything's going to shake and everything's going to move quite dramatically, but maybe that's not the case. If my machine were out of balance, that would cause more emotional force, and I would touch the machine and I would feel it's vibrating, no problem. Obviously, I need to quantify that and measure that. But if I had a bearing problem, that's not actually going to cause the machine to move and vibrate excessively. It's going to be more localized impacts, shocks, actually due to the bearing that might be damaged. So that's a different heartbeat entirely. Maybe the rotor bars have got a different heartbeat. Kind of bring them all together, and it kind of gets a bit more complicated. Maybe that's a bit loud, sorry about that. But obviously the heartbeats combined together, we measure these heartbeats distinctly with our vibration sensor at key strategic measurement locations, and we can trend and track each component within the machine. Okay. So just a little bit of theoretical stuff here before we kind of move forward with some signals and understand how these heartbeats produce themselves. One of the key aspects of the story with vibration condition monitoring, we're trending and tracking the health. And what's most important, obviously, is that we measure the amplitude, how good, hopefully, how small the vibration is, or how large it might be because our machine has a problem. The amplitude is important, but the change in amplitude is important as well. Condition monitoring about looking for change, trend and track the health and look for change. Once that change occurs, we can say the vibration has changed due to what? Well, that's where we need to understand the frequency, the rate of the heartbeat. Is it 25 pulses per rotation? Is it 6 pulses per rotation? Or is it 1 pulse per rotation? Depending upon what's causing it to vibrate. So the frequency enables us to understand the nature of the fault, the source of what's causing this thing to vibrate, the defect itself. Is it the bearing? Is it the blades? Is it the coupling? And so forth. And then maybe understanding how a machine might move by understanding the motion would actually provide us with more diagnostic information to narrow down the problem. So if we take a look at the basic initial part of the signal we measure, it's the waveform, forgive me, sorry about that. With this simulator here, I can just start this machine up and just bear with me a moment. I can see that this shaft is being displaced. I've got a clock gauge to visually show you what normally a vibration sensor would do. We might use a sensor placed on the body of the bearing. It's measuring the vibration within that bearing. Just pop that clock gauge back on again. So obviously if my shaft had a fan on it and there's a heavy spot, it's going to cause it to vibrate at a frequency of once per rotation due to the heavy spot. If the heavy spot gets greater because product's building up on a fan blade maybe, then obviously what will happen is the amplitude, the level of the vibration will grow. And just be steady there, I'm going to wipe that bearing if I'm not careful, just wind that back a bit. So we can see that the amplitude of the signal now is grown due to a heavier mass on the actual fan, maybe that's mounted on that particular shaft. So that's good. If the speed changes, then obviously what's going to the signal? The waves get closer together. So the speed increases, but it takes less time to do one full rotation. Less time. So one thing that's very important about vibration is that we measure and we correlate speed with the signals. And with today's technology, that's normally quite a simple task to do. So that's a very important point. The speed is a critical measure that we need to understand. So, what do all those peaks mean? Kind of vibration people look at signals and heartbeats. How do they know, what the dominant frequency is? Where is it coming from within the machine? In reality, Due to the complexity of the fact that I've got electrical vibrations, I've got process vibrations maybe here from the air going through the ventilation system, I've got mechanical vibrations inherently in the machine, the waveform is very complicated and difficult to maybe relate to. But thankfully, there is a way to simplify this to make what is a complex signal a much more simplified signal. Mathematically, it's a very involved process, but thankfully, due to technology today, it's actually not that difficult in a graphical way, and indeed for the analysts to very quickly interpret the results. So here's my wave. Here's the wave. If I increase the speed there, just to make it a little bit more, just running slightly quicker, speed up, speed that fan up. This wave, the rate one cycle of the signal represents one rotation of the shaft. Okay. So obviously, as the imbalance grows at a fixed speed, now the speed is now fixed, the imbalance grows or it weakens because we clean the fan, the shape of the wave, the amplitude will grow or weaken as we improve the balance. So what do? Well, as you saw just now, that waveform was very complex. Well, let's make it easier. Let's ask you this question. Here's the wave. I'm looking now at that signal. I'm looking 90 degrees at that signal. What do I see? The end of the wave. A line, a peak. So in simple terms, vibration systems today take the signal initially like this, which is currently very simple, and they convert it to a frequency spectrum by initially upturning that 45 degrees, and then if I complete the 90-degree rotation, what do we see? One single peak. What do I see looking at 90 degrees? I see the wave. So we take the time wave and we convert it to a frequency peak. Very crisp, very sharp way of presenting the data. This peak here would be proportional to rotational speed. Let's kind of just switch it back again. And maybe the bearing here has a defect. Okay, so the bearing's got a pitted spool point on the bearing. And in one rotation, there'll be a certain number of pulsation forces every time a ball strikes the bearing. Count the number of pulses there if you wish to. Higher or lower frequency? Higher frequency, yeah? So the green wave is the heartbeat of the bearing. Let's bring that together. Just click on there, sorry about that. There we go. Let's put it at 45 degrees. What do we see? Two separate peaks. One proportional to rotational speed, the unbalance in the fan, and one that shouldn't be there because there shouldn't be a problem with the bearing, but it's appeared at, 6.1 times the speed. Not 6, not 7, but 6.1 times the speed, for example. So that's a key difference with the bearing. It's actually not a whole number. So these peaks, we can separate them from a very complex wave and trend them discreetly to know what's wrong with the machine if it's vibrating too much. So with knowledge, we can look at problems with spectra, and this might be a normal reading. There's hardly any other peaks in the spectrum. Quite a low level running speed peak, which is very normal to see at low amplitude. Happy days. A heavy mass sticks to the fan. That frequency will grow, the amplitude will grow, and we'll know exactly what's caused it. Our software, we click on the peak and we're told it's once times the speed. As we'll see in a moment, maybe if two shafts are not aligned, so two shaft motor pump should be perfectly aligned, but maybe one is shimmed higher than the other. Now think about the forces, think about the motion as it rotates, one rotation. One pulse, two pulses. One pulse, two pulses. So two heartbeats, two pulses per rotation, producing a very distinctive characteristic second peak. An imbalance would not underline do that. It's completely different. So different faults, different defects, different problems that develop show a distinct difference in the appearance, in the frequency spectrum, in the heartbeat of the machine. Here there's obviously several peaks. If we have a problem with a bearing, for example, this data here is showing me a small 1x peak that's normal, but these bearing peaks should not be there. End off. Sadly, it's a vibration reading, they're present, the damage is done. This peak here is at 3.1 pulses per rotation. If I click on that in my software, it would tell me it's occurring at 3.1 times the speed. If it's 3 blades, it would be at 3 times the speed. If the blades were problematic, but here it's 3.1. So that's indicating maybe a bearing. Okay, so the spectrum itself works nice, you know, in one single peak, maybe easier, you know, I can look at that, I can see one peak. But the reality is machines don't produce just pure smooth vibrational forces. Some of them can be shock, we've spoken about those. Some of them might be, you know, pushing and pulling forces against each other with two shafts that are fighting each other. So that's going to cause the data to distinctly change. And there's other techniques, which I'm sorry to say we don't have time to cover today, but you know, there's other supplementary techniques that do support the analyst in diagnosing problems. So where the vibration is smooth, in summary, what do we see? You know, a heavy mass rotating around the rotor, you know, a strong radial force, an increase in vibration at what frequency? Once times the speed. So an unbalance in a system will actually occur at once times the speed. Little else present, that's the main problem. Other peaks might mean there's a second problem. Here, the vibration is going to change in behaviour. It's not such a smooth force. You've got two shafts fighting one another. It might be bolted down, but think about the stress and forces being exhibited on that machine. So that's going to change the shape of the spectrum, the frequency spectrum, where we see maybe more than just one peak. Here we're seeing three particular peaks due to non-linearities, distortion of the wave. Instead of being nice and smooth, it's distorted. That fighting force is causing that distortion. Here with shock, kind of I always take that scenario, take a stone, throw it into a pond, you kind of get the impact of the stone, and then you get the echo, the ripple. Here, shock might be quite small, intense shocks. Here it's maybe quite visually strong, exaggerate, but that will change the shape of the reading we see, the spectrum, the frequency heartbeat. Shock could come from bearings. Shock could come from loose shaft on the bearing, so it's working loose on the shaft. That would cause shock as well in the signal. That produces distinctly something uniquely different. Characteristics that we call harmonics. Lots of them. Here we've got 7. Typically we see actually a lot more where something might be loose. Harmonics, like the echo kind of scenario, are equally spaced peaks that appear in the spectrum, equally spaced peaks. So that's, you know, distinctly different to what you saw just now with a smooth vibration where there was only one single dominant peak. One other factor, maybe one step too much here, but let's just scratch the surface. Another characteristic in the reading we call sidebands. What's the difference? Well, look at these gears. Look at how the teeth at one part of the rotation come right into the root of the teeth, then the gap opens. So that means the vibration, once the rev goes strong, goes weak. Goes strong, goes weak. As it comes deeper into the root, the amplitude of that wave and the signal being produced will go strong, and where it separates because there's not so much force, the strength of the signal will weaken. That causes a distinct behaviour in the spectrum, maybe the next one, called sidebands. These are equally spaced peaks, either side a central peak. So here we have several peaks equally spaced either side of the centre frequency. So they are spaced by a delta, a difference in frequency that's known, and they're equally spaced. And they're common on bearing problems, gear problems, looseness, maybe bearings and gears. Maybe electrical problems might be another one as well, where we see that distinct behaviour. And again, there's some more sidebands. Maybe if the defect here, think about this, the defect, that red dot, is inside the bearing, there's a pitted damage spot. When the defect enters the lower part of the bearing, due to gravity, the forces are greater. So we get a stronger signal. Then as the defect travels out of the load zone towards the top, the signal weakens slightly. Then it goes strong again. And that will cause, as we said just a second ago, a distinct pattern, sidebands. But we've got shock as well. So what do we see? Shock results in harmonics, equally spaced peaks, the larger ones there in yellow, and sidebands where we see equally spaced peaks around those harmonics. Maybe that's one step too far for those of you that maybe are newer to this subject, but distinctly different pictures to simplify. Okay, we've got some examples here, some case studies. I think I have time to maybe choose. There's probably 2 minutes to go through them all, but so I'm just going to go to this particular one here. So this is a hammer mill bearing on a particular bearing on a motor. There's the actual drive itself. So this mill crushes or mashes wheat in preparation for bioethanol fuel producing process. Variable speed motor, so it varies in speed during operation. And monthly vibration measurements were collected when the plant first started up in 2010 and continue to monitor this machine up to present day on a monthly basis. Now, this trend is a trend actually of the shock within the machine, the impact force, the shocks that might be produced from a bad bearing. Well, this is the trend of the shocks, where at the baseline, the first measurement taken here, which may not always be the baseline actually, doesn't always mean it's good because it's the first reading, but it's 5G. Well, that's kind of quite reasonable. It's a peak-to-peak measurement of the shock of the signal, up to 70 Gs. You can see the degradation there is at up to 70 Gs. And then you can see after repair that the levels returned to normal afterwards. What's this? Well, this is the frequency heartbeat of a particular point on the machine, the motor drive end or motor inboard bearing here. So this is the bearing at the motor drive end. And you can see the heartbeat month on month here. The most recent reading back when the problem was present, being at the back, how the heartbeat has changed. The heartbeat has changed. If this was a problem with balance, for example, that was lower down the scale. My 1x peak is this kind of very small peak down here, not of concern. But these stronger peaks here are, the main cause of why that trend caused that kind of degradation. So here we can see the actual singles spectrum, the heartbeat, the frequency spectrum from that particular point. And in this case, we can clearly see, due to the purple dots there, harmonics are evident within that particular FFT, the spectrum itself, the frequency spectrum. Equally spaced peaks, clearly evident. The point is, what is the rate of those peaks? What is the spacing between? Well, the driving frequency, the first one, is at 3.05 times the speed. So let's just round it up to 3.1 times the speed. Not 3, but 3.1 shocks per rotation. This particular case, the bearing was known. The bearing was known. We knew it was a 6322 bearing. And in that case, that correlated with these dotted lines that matched the outer race frequency of the bearing. So we knew exactly that it was the outer race of the bearing. Okay, some might think we don't have the bearing number in all cases, not a problem. What else could cause 3.1 shocks per rotation on a pump, motor assembly, a grinder here and a motor? Apart from transmitted vibration from somewhere else, perhaps, which it wasn't because it was only present at the motor, electrical vibration could cause a strange number here. Well, it wasn't that. It had to be a bearing. So we would have known anyway. So there's the actual bearing that was taken out. There's a very distinct wear pattern in this bearing as well, which provides the analyst with root cause information. Because it's not just about detecting the problem, really. Condition monitoring only trends and tracks the defect. To improve the actual condition, improve the reliability, we need to ask why. What caused it, and what action we're going to take, rather than just say, put a new bearing in, what's caused it. Let's put that to bed, as well as obviously install a new bearing. And I think since that time, after replacement, that's continued to trend quite happily to present day. So let's check the time here. So I've got maybe more time for one more. Slight different twist of the tail here, actually. This problem is maybe not quite as common on general plant, but on certainly larger drives, it has a place where it could occur. This is more maybe common for a larger drive, not small, 1.5 kilowatts, but large machines. This is a motor driving a centrifugal fan. It's a gas recycle fan. You've got your motor obviously with your two plumber block Cooper bearings here, and then your coupling is just under this guard here. So again, this machine I believe has been trended periodically since 1999 on a monthly basis when the plant runs during their operational season. Bit of detail there about the machine, 315 kilowatts, 1500 RPM less slip. So my general vibration trend, according to an ISO standard, actually was well within a tolerance. But because it's important not just to trend the general level of vibration, perhaps different parts of the vibration, i.e. the different heartbeats, you can trend them independently. This particular trend segment here obviously violated an alarm. Drilling down slightly deeper into the data, you can see the degradation. This is one particular point. Again, this is on the motor non-drive end. So this particular measurement was taken at the non-drive end. The most recent reading taken at the time this was a problem is at the back. And you can see the visual picture there has changed where you see obviously more activity at the back, harmonics. So there they are in a bit more detail. We've zoomed in there if you like and just taken that one spectrum out. But upon further investigation, we took a higher resolution measurement, like on your digital camera, you take more pixels. If we take more lines, we get clearer, sharper, crisper peaks. And it revealed, actually, that we had harmonics, equally spaced peaks, and equally spaced peaks either side of a central peak. So we had harmonics and we had sidebands, which fits with what we discussed before. We had both. And you can see here, this is the signal in raw form, very complicated, very difficult to relate to, but the picture is it goes strong, it goes weak, it goes strong, it goes weak. The amplitude's changing, that's why there's sidebands. The harmonics are there due to distortion. Zoomed in a bit more around those main peaks there, and understanding the spacing of the sidebands was the final part of the jigsaw. So the spacing between the central peak and the peak spaced equally either side, the difference, the delta frequency was the key. The spacing was 42 cycles per minute, or 0.7 hertz. And then with some known mathematics that, to be fair, the software today deals with this for you anyway, but mathematically, this tied down to a rotor bar problem. Not a bearing problem, not a balance problem, not an alignment problem, but a rotor bar problem. And thankfully, the frustration can be we don't always get the feedback, but we got feedback on this from the actual company. They took it on board, they planned the repair, sent it away to the remote repair shop, and that is the damage of the broken bar that caused that distinct particular heartbeat. We knew it wasn't the bearings, we knew it wasn't the fan, we knew it wasn't the coupling, it was down, in this case, to the actual rotor bars. Okay, so I guess I'm just getting on my time there. Just forgive me, I'll just skip to the end. I don't think I've got time for another one. So, in summary, vibration is a useful tool on generally rotating equipment. It's fair to say, supplemented maybe by high frequency methods. It can detect a wide variety of different defects on rotating plant, and understanding the actual signals, the heartbeat is the key to understanding what's causing the problem, and then judgments can be made as to when you're going to do your corrective actions. So happy days. I can't believe I've kept that within the 30 minutes, to be honest, but it's gone so quickly. But for myself personally, that's a thank you, but I welcome any questions.